Hello, everybody. So I am Tapo Mayuk Bhattacharjee. If you find it difficult to pronounce it, you can just call me Tapo. I'm a postdoc at the computer science department at University of Washington in the Personal Robotics Lab. A postdoc is basically, if you're not familiar, it's like after your PhD and before you go do something in the, like either in academia or in industry. This is like a period of advanced training. And at UW-CSE, research associate is just a fancy name for a postdoc. So yeah, and I will be joining as an assistant professor at the computer science department of Cornell University next fall. I just deferred my joining because of all these different uncertainties. So I work on assistive robots, and today I'm going to present to you about robot-assisted feeding. And in general, basically, I'm going to look at, in general, assistive robots. So before I go into the details of the talk, I should say that this is this work would not be possible without the help from all of these people. This is our current lab, and this is the robot Herb that you see. And here is my PhD lab. And this was a lunch we went to after I defended my PhD. So since we are here, we are eating, I'll start by showing a recent result on robot-assisted feeding that we had in our lab. So here you see a robot mounted on a wheelchair, autonomously going, picking up a tool. In this case, it's a fork, and it goes then on top of a plate. It identifies different food items there, figures out using algorithms what is the best strategy to pick up, figures out how much force it should apply to pick that food up. Then once it picks it up, it goes in front of the person, looks at the face, detects the mouth is open and other things, and then comes close to the mouth and orients the food so that it's easy for the person to take a bite. So the entire thing that you saw here is autonomous. And we have built this in our lab, and I'm going to talk about this as well as some other projects that I have done. But I'm not only interested in these technical challenges of these manipulation, human-robot interaction, and as well as perceiving objects in the real world, but I'm also very interested in evaluating them with real users. And in our case, our users are people who cannot feed themselves. So people with mobility limitations. So here you see the robot feeding people with spinal cord injuries from different, C1, from C1, C2 to C6, C7. These are just different levels of spinal cord injuries, and depending on the level, their mobility limitation is different. So from these two videos, you can probably guess that I work on assistive robots, and my goal is to enable robots to assist people with mobility limitations with tasks of daily living. Now, if you look at tasks of daily living, what do I mean by tasks of daily living? Actually, in literature, there is a very clean definition of these activities of daily living. And according to a survey back in 2010, there is around 12.3 million people in the US alone that needed assistance with these activities, right? But if you look at this picture, right, they are so different. Like the caregivers are assisting these care recipients in many different tasks. So what is common? If you think about it, to be able to successfully do these tasks in each of these images, as you see, the caregiver needs to physically interact with the person or the objects around on the caregiver. So basically, physical interaction is inevitable. And so the fundamental research question that I'm interested in is how can a robot leverage physical interactions in unstructured environments to assist with activities of daily living? So through this talk, I'm going to cover some ways that we have achieved this. The talk at some points will be high level, at some points it will go a little bit deeper, but at any point of time, if you have any questions, let me know. So our approach to be able to do this is twofold. First, we want to infer the properties that the robot comes in contact with, right? So for example, if the robot comes in contact with this bottle, can I tell that it's a bottle? And then I want to infer these, basically leverage these properties that we have learned to perform the tasks. Because now, if I know it's a bottle, can I use that information to actually perform the task? So this is the outline will cover both of these aspects. And so the first part of the talk will focus on inferring object properties, where I will just focus on general, general applications. And then I am going to, the second part of my talk, I'm going to focus on the application of robot assisted feeding that I talked about before. So let's first focus on inferring object properties. So let's go back to this diagram, right? Like what do we see? If we let's dive a little bit deeper to this. We see that some of these physical interactions where the person, the caregiver, is touching the environment, whether cutting food for meal preparation, cleaning something, or feeding someone, right? It can either, the person may touch that person either using small area or using large area. And so there is variable contact area that we need to deal with, right? And this is a little bit different than general robotic manipulation literature, where we just consider grasping with the end effector. Because here the person may come in contact with the caregiver, can come in contact with the care recipient over their entire arm. So the contact area can be large. It also can be brief. In fact, we want it to be brief because we want the robot to be like very reactive, right? And sometimes it can be opportunistic. What I mean by that is, say, like on your table, sometimes you want to grab something. While grabbing something, your rest of the arm can come in contact with the table surface or something else. So those contacts are not intended, but they are opportunistic. So even from those contacts, can we tell something about it? So physical interactions, because all of these things are inevitable, this makes these assistants, these physical interactions unique. And therefore, it makes it also very challenging because the actions are not optimized for sensing. And sensing depends on action. What do I mean by that? What I mean by that is, let's say I touch this bottle, right? I'm closing my eyes. So I have only the haptic feel. So I can explore and feel the bottle, and I can tell, oh, okay, this feels like bottle. It probably is a metallic object. It has a metallic, it's made of metal and things like that, right? But in our case, especially when the contact is brief, we do not have the time to explore. So the robot needs to be able to make these decisions immediately, and it depends on the sensing. And the sensing depends on the action, because if I say, okay, this feels hard because it feels, it's giving me resistance, but something else feels soft, it depends on what you sense, right? How you are acting. So if I hit the object harder, I will get larger forces. So a larger force doesn't just mean it's a hard object, because it depends on how you act. In addition, home environments are very unstructured, and some interactions are hard to model. So then the first question that comes that, okay, how do we collect data? And you can say, okay, why do I care about touch? Why do I care about physical interactions? Can I just not use vision to do it? So here is a slide for you. If you look at these two objects, what do you think? Probably you will say that the right object is a cherry tomato, and the left is a ceramic plate. But if you could touch it, you would actually know that they are neither. Like the right object is actually made of plastic, as well as the left object. So let's use touch. We humans, we use touch all the time. Let's use touch. Touch can give us a lot more information. And I'm not saying let's not use vision. Let's use both, but also let's use touch. In fact, it's not just about more information. It is inevitable. Like if I want to use my robots to help people with disabilities, I need to be able to, you need to be able to touch them to be able to actually do. For example, if the robot is trying to pull up a blanket on Henry here, who's a person with quadriplegia, you have to be able to touch the person or the bed. You cannot avoid contact. So we need to be able to sense contact. But the key insight that I have through my research is that contact information is not just force. When we talk about contact, generally, if you look at robotics research, you will think, you'll see that it's just force, but it's not, right? Most of them focus on force, but it's more than that. Basically, it's multimodal. And today, today I'm going to focus on two of those modalities, force and thermal. So let's focus on force first. So let's say you have this kitchen environment. You have some soft objects and you have some hard objects. And some of these objects can move. So to be able, for a robot to be able to physically interact and tell which object is what, whether it's hard or soft, whether the object has moved or not, we need to collect data. But collecting data is hard here because to collect data, you need to actually bring the robot there and make them touch different things. It's not like anybody can take a camera and take a picture wherever they go. You have to actually physically take a robot and make physical interactions. So collecting data for physical interactions is actually hard. So what we did was we started in our lab. And what we did was we had an artificial skin sensor. Just like we have humans have skin, we have an artificial skin sensor for the robot that we put. And this skin we did not develop, we bought it. And we put it on the robot. And here on the right, you can see the visualization. So darker pixels means higher forces. So it's like a 24 by 16 array, and it's rolled. So if you unroll it, it's like a rectangular array, right? And here, like as the robot touches, whichever pixels get activated means that's where the contact happens. And darker pixels means larger forces. But the problem with this sensor is that this was only covering the forearm because it's rigid. But if you look at human arm, we have skin all over our body. Like for example, if you say like you have skin on your wrist, right? And I move my wrist, I can move the wrist and the skin stretches and folds. Just like that, the robot has joints and it moves. And so we need something that is stretchable and flexible to be able to cover the entire body, right? So in our own lab, we developed an artificial fabric-based skin sensor, which is basically a conductive resistive fabric sandwiched between two conductive fabrics. And each of the squares that you see are taxels, we call them taxels, like tactile pixels. So if now you can use this fabric, it's like a sleeve. So you put the sleeve on top of the robot. And now if the robot goes and touches different things, it can actually feel it because through the skin, I can tell not only how much force I am applying, but also where in my arm I am contacting, right? And so using all of this data, we started with a very vanilla model, like a hidden Markov model, and we modeled them to figure out how to, like, can we use this data to say hard versus soft object or whether the object has moved or not.
Tapo, sorry to interrupt, but I just had a quick question about the taxels you just mentioned.
Sure.
So so I know pixels are able to, and like basically save like visual information. Is there kind of a way to save tactile information so that you, instead of like having to bring the robot to each object, you could have one general purpose tactile simulator that you could use, like you could record the tactile information and then use that later on to simulate a huge variety of different kind of tactile properties?
Yeah, that's a great question. So this is actually a tactile sensor, right? So it doesn't have cameras. It's a skin, artificial skin. So when you go and you interact, like you touch the object, then you get the data. But if you want to simulate these interactions instead of exactly as you said, like for example, instead of having the robot go and touch different things, if I can simulate a tactile sensor and objects and then create simulations of these forces, then do we need to touch? And that's where the problem, it's a very environment dependent answer. So for example, if I have a rigid object and a rigid sensor, I can model this as as a collision between two elastic materials and elastic objects. And we have done that. And you can create simulation for that. But for example, if I want to model interaction with a deformable object, like a piece of cloth or food, for example, that's very difficult to model because they are not homogeneous. Like for example, a food, like think of a cake. It has different layers with different moduluses of elasticity, different topologies, many different things. And so those things are very difficult to model. So the simulation data is generally not very high fidelity. That's why we need to collect real physical interaction data. Hope that answers your question.
Yeah, thanks, Tapo.
Cool. Okay, so coming back to that, so we use this hidden Markov model to label these different labels, right? Like hard or soft objects and other labels that we are interested in. So let me show you how it works, right? Like using a skin and force sensor, what can you do in manipulation? So to test it, we created this artificial foliage environment. Why did we create foliage environment? Because foliage is very cluttered. Even if you want to use vision, you cannot see through it. You cannot see what's going on inside. So we created an artificial foliage, basically with tree trunks and leaves. And even though in this picture you see camera, the Kinect, and other things, we are not using the camera here, right? And the goal for us here was that the robot needs to go and pick up a keychain from inside this forest, this foliage, okay? So now, the robot doesn't know anything about the environment. It doesn't know where the trunks are, where the leaves are. Only thing it knows is where the keychain is. And it needs to go, and it needs to avoid the obstacles, right? Or at least make sure if it can somehow reach, because avoiding obstacles here is impossible. It's very cluttered environment. So here is the video of us using all these algorithms to actually do this. So here on the left, you'll see the robot first tries to just go straight because it doesn't know that there is no trunk. When it goes straight, the skin, the blue part, comes in contact with the trunk. Using hidden Markov models, we know that it's hard. And then it models that using those brown dots that you see on the right. If it touches a leaf, it knows it's soft. And so as you can see from the elbow, the arrows on the elbow, and it knows it's soft and it can push through it. So it doesn't push, it doesn't put it there. So it only puts the hard points. And these points then go on top of basically a motion planner uses these points and continuously replans to avoid the obstacles. So let me explain again. Everything that you see here is autonomous. Human is not controlling anything, right? Robot doesn't have any idea of the environment. So first it goes straight. It detects it's a hard object. So the planner knows there is a hard object there. So next time it tries to avoid around it. When it tries to avoid, its elbow comes in contact with the leaf, but say its end effector, like at the tip, comes in contact with the ground. It knows the tip is rigid, but the elbow area, that part, the object is soft. So it again updates its estimate, and the planner now, with more of these points, knows where the hard objects are, and then it snakes around it and goes and picks up the like a keychain. So you can see that using interesting combination of perception, like basically using haptics, even without using vision at all, and distributed haptics, as well as motion planning and controls, you can do these interesting manipulation things completely autonomously in these cluttered environments. But so far, so you see here that here we have seen so far that force modality can be useful, right? And we can detect these different labels. But is force the entire story? No, right? Because as I mentioned, contact is multimodal. So for example, if we just had forces with us, we probably will have a lot of difficulty in detecting between this glass, like for example, this plastic bottle or this tin can, or this metallic, like this glass bottle or something else, because all of them may give similar forces because they are all rigid. But if you were to touch them, maybe you will realize that they have different thermal properties. So thermal can also be an interesting signal, right? So what do I mean by thermal? Well, all of us, we know about this passive thermal sensing, where you just put a thermometer and the thermometer tells you how, like whether someone has a fever or not, right? It measures the temperature of the object that you are touching. But tell me something. Why does sometimes metal feels colder than wood when you touch them. It doesn't mean they are in different temperatures. They are in the same temperature in the same room. But what happens in metal is the human finger generally is at a higher temperature because of the blood flowing through it. And the metal is at the room temperature. But because of this temperature difference, heat is sucked out from your finger. And the rate at which it is sucked out, it depends on the thermal properties of this metal. And for example, thermal effusivity, which is much higher for a metal than wood. And so heat is sucked out at a higher rate, and so you feel colder, right? So the difference with passive thermal sensing here is that here your arm, your thing is, your sensor is heated. So it's active, right? And so the idea is that can we develop this active thermal sensor, a heated sensor, and put it on the robot? And see, in addition to force, can we get even more properties, right? So if you look at this picture, we found that actually, yes, the thermal data looks very different. When the sensor touched aluminum, wood, or human skin, you see how different the data looks like. Any easy machine learning algorithm, not even machine learning, it's a simple regression or anything like that can tell the difference between this. But the problem is, look at the x-axis. The time scales are very high, 25 seconds. I mentioned we do not have the option of using so much time when we are interacting with people. So we need to be brief. So we care about only this time scale. And the data can become very noisy because the interactions, like the initial conditions, may not be the same. So even in this kind of cases, is it possible to use thermal sensing? To figure it out, we actually collected data in our lab with different material samples. And we found that yes, even in the short time window, it is possible to just within like 0.5 seconds of interaction, you can tell with 84% accuracy difference between these 11 materials. And now coming to your original question, Saket, we actually thought the same thing. It's very difficult for us to collect a lot of data from this. So we used simulations for this. And so we basically modeled this thermal behavior using semi-infinite solid. I'm going to go into the detailed math of this. If you have any questions, you can ask me later on this. But basically, the insight is that heat transfer between a sensor and a bottle and a block is a function of three things. It's a function of the distance of the sensor, exact thermistor from the surface, like the interacting surface. It's also a function of the thermal properties of the sensor and the thermal properties of the object. And we can get all of these things either by calibration or from the manufacturer from where we got the sensor. And for the objects, we can use online databases. So using this, we simulated these data. And as you can see, the red dashed lines are the simulated ones, and they are pretty close to the experimental ones, right? So using this, we could get more intuition about what thermal modality could do. So you can look at this graph, and I can tell you, basically what it means is each of these nodes are materials, okay? And if there is a line connecting between these two materials, that means it's difficult to tell the difference between these two materials using thermal sensing modality. So we basically, what it says is, it is using thermal sensing, you can tell the difference between aluminum and wood because there is no direct line connecting between them. But it is very difficult to tell the difference between aluminum and copper. So this gives us a very good intuition that, okay, if I were to develop a robot and this is my target, what kind of sensors I should use? Will thermal sensing be useful, or should I use the force sensing that I showed before, right? So now that we had this, we thought, can we always distinguish wood from aluminum as it says in this graph? Turns out, no. It actually depends on an assumption that they are in the same initial temperature. What I mean is, say if you tell a robot, hey robot, go and pick up a wooden bowl or pick up a metallic can from the same room, you can do it, as shown by the graph. But if the wooden bowl is inside the refrigerator, it's in a different thermal condition than the metallic can, which is outside, then it can become confusing. And we found that, again, I'm not going to go to the math, but basically what we found is using math, if we can predict what that condition is. And so what we did in this experiment, it was a very interesting experiment, which is using our model, mathematical model, we predicted when this will be confusing to tell the difference between metal and wood. And then in that temperature, initial condition, we cooled down the wooden block for that temperature that was predicted by the model. And then we called people. We blindfolded them so that they don't see what they're touching. And we asked them, tell us, what are you touching? Are you touching a metal or a wood? And consistently, people misclassified cold wood as metal. So as you see, it is dependent on initial conditions. So what we find from here, that means what the question is, then how can a robot pick up a wooden bowl from inside a refrigerator? So that's where we came up with an intelligent sensor design, where we used both passive and active thermal sensing side by side so that it can also tell the environmental temperature. Using this, we can tell the difference. Remember, this is difficult for us humans to do, but by intelligent sensor design, we can overcome this difficulty of human sensing so that the robots can actually do more than what humans can do. So now, having said that, we see that thermal sensing can also be useful, but it's complementary to force, right? Because force can be useful in certain cases, but thermal sensing can be useful in some other cases. So then the question obviously is, let's combine them. So we developed this skin sensor that I showed you originally, artificial skin sensor. But in addition to force, now we added thermal as well. And we put it on the robot, just like a robot is wearing a shirt, like a sleeve. And then our goal, if you remember, my original goal is to help people in their real homes with assistance. We asked people, where do you need assistance with? They said, I want the robot to help me in my bedroom, in my bathroom, in my kitchen. So we took the robot, we put this sensor on the robot, and we put it in a person's real home for multiple days and collected data in a bathroom in different objects, with different objects, in a kitchen, again, different objects outside in a kitchen sink, or inside refrigerator, or even in a bedroom, like touching on the bed, on the table, so many different objects over multiple days. And there was a lot of variability in the data collection. We also touched humans because, as I mentioned, to do tasks, you need to be able to interact with humans, right? And again, what we found, and this is the key takeaway of this part of my talk, is that when you combine these different modalities, we can always infer more properties than, like, for properties such as what material the object is made of, what object it is, and things like that, than using a single modality alone. So the key insight that I want you guys to take out of this part of my talk is multimodal sensing is very useful because they have complementary capabilities. So let's not just rely on one sensing, especially when we want to interact with objects in an uncertain environment, like an actual real home. Let's leverage their strengths to capture more information. And we can actually benefit by exploring non-traditional sensing modalities, such as thermal sensing or other sensing modalities.
So sorry to interrupt again, but like kind of building off of that, is one of the modalities like texture? Because earlier when you mentioned like the distinguishing between like the wooden bowl and the metal, sometimes you can distinguish between objects that have the same temperature just by the texture of it. Is that a modality you guys are using?
Yes. So basically, as I mentioned, it's a very multimodal thing. And texture is basically, you do it using the tactile modality itself. So let me explain how it works, right? So say texture, like say I have this, my phone, right? To find the texture, the way you do is, so there are two kinds of texture. Like one thing is, okay, just by visually looking at it, can you tell the texture? Yes. That is just, you can do it using visual modality. But that's kind of like because of the surface irregularities that happens due to the texture, you can tell some of these things. And you can do that with the visual modality. But many times it is possible to fool the visual modality, even if the textures are different, as I showed you in one of those slides, initially in the motivation slides, right? And so for those, you can use the tactile modality where you touch an object and you see, you think you do it all the time, right? And you explore it. Like, for example, if I just scratch the surface, I can tell whether the surface is rough or smooth because of these high frequency oscillations that we get when we scratch across it. And we use it all the time. For example, if I want to go and buy a shirt or something, and I want to see how smooth it would feel, I will touch the textile and I'll rub it to feel the texture. And only sometimes just looking at it is not enough. So using the same tactile modality, you could infer texture as well, but you will have to use a different, you cannot just touch it and leave it. You will have to do an exploratory behavior where you scratch the surface to get these high frequency oscillations out of it. Does that make sense?
Yeah, that makes sense. It's a great answer. Thank you.
Cool, thank you. So, okay, so now let me jump to the next part of my talk which is basically how I motivated my entire work, which is how, now that we know how to infer these properties, how can we leverage these properties to actually perform an activity of daily living and help a person with mobility limitation. So for that application, we chose feeding. So the question is, why assistive feeding? Again, because there are millions of people in the United States alone that need assistance with activities of daily living, right? Now, caregivers are playing an amazing role, but even with their help, care recipients still feel embarrassed, rushed, and socially challenged. And these are not the adjectives that I made up. I actually went to these facilities and asked them, interviewed them, and that's what they told me. It's also, if you think about it, it's natural. Like, imagine yourself asking someone else to feed you every morsel of bite in your day-to-day life. It takes away the sense of control and independence from you, right? And you want to be in control of what you are doing in your life. And so the robots can play a very important role, because if the robot, the initial video that I showed, the robot arm, the person can think of this robot arm as an extension of their own arm, and they would feel like they are actually doing the task themselves, right? So this is why we chose this task, to showcase the robotic capabilities. How can robot help these people in their daily lives? So then the question is, let's look at how to actually do the task. You may think feeding is easy. Well, I thought so too when I started the project. But let's look at this person picking up, this bowl, like food items from this bowl. There are so many interesting strategies. Like, you reconfigure the food items, you pick different food items in different ways. Food items are of different characteristics, right? And so the question is, how do you even program a robot to actually do this? And this is just one part of it, picking up. You also need to feed someone to transfer the bite, right? And what we found out is we actually need the robot to be intelligent and autonomous, because the robot cannot, it's very difficult for the person to completely control the robot and do these tasks. We actually surveyed one expert user of a robot arm, and this person said, I can use the robot arm to open door or pick up a book, but feeding is such an intricate task that it would take him 45, he said, it would take him 45 minutes to just pick up like 3 items, solid food items of food items in a plate. So we definitely need an intelligent autonomous system, right? So then we thought, okay, let's try with the simplest approach. We attached a fork to a robot, and we just thought, let the robot just go vertically. Even if the person is doing all of these complicated things, do we actually need it to pick up all of these things? Let's just use a simple method, right? And so for that, we did this, and we found out that yes, a simple strategy can pick up a food item, and it's not that difficult. But when we wanted to extend the variety of food items, that's where we found that it becomes very challenging and it fails for other food items. And this is because robot-assisted feeding is a very challenging problem, right? Like, bite acquisition is challenging because you have to perceive the food in a cluttered environment. You have to manipulate food in a very different food items with many different characteristics, right? And in addition, you have this bite transfer where you need to think about handing over the food to the person's mouth. And it should be easy for the person to take a bite. And so it's a very challenging problem to do. right? So we thought, okay, then how do you even create a robot to do this? The one realization we had was that we humans eat all the time. Like we eat breakfast, lunch, and dinner. So let's just study what we ourselves do. So in our lab here at UW, we brought in people. We gave them probably the most expensive fork that they would ever eat food with, instrumented with different sensors as well as motion capture markers. And we told them pick up different food items, and we collected data. And we found that there are some very interesting things we learned. So for example, say for picking up the banana, banana is so slippery that if you just go straight and pick it up, gravity will just bring it down. It will slip off the fork. So, and this is exactly what happened for this person. But the person subconsciously changed the strategy so that the fork goes at an angle. Now, if you think about physics, what happens is if the fork goes at an angle, the gravity vector creates a frictional component, and that keeps the food on the fork. So it's so many interesting strategies like this that we could find that what humans do when we looked at this data. So based on this, we developed a taxonomy, and we found that, and we found out what are the different actions that people use to pick up food. But it's not just the motions. We also found that people use different forces. For example, the force with which I will skewer a banana is different from the force that I use to skewer a grape with hard skin and soft inside, or a carrot, which is very hard. In fact, they are so different that just using 0.7 seconds on average data after interacting with the food, using a machine learning algorithm like a temporal convolution network, we can tell the difference between all these food categories just using force. So imagine how informative forces are. So now that we see this data, we could tell why the robot failed. It was because our robot was using the same policy, control policy, to pick up food items. But humans use different control policies. So let's develop different control policies depending on the kind of food item. So now that we want to do that, we thought, okay, let's try to develop the robotic system. So the first step is hardware. So we chose this hardware where we basically had a robot arm mounted on the wheelchair. Why did we choose this hardware? Because we wanted the robot to go with the person wherever the person goes. Think about it. A person may want to be fed not just in their own dining table in their home, but maybe at a friend's place, or maybe even at a restaurant. If the robot moves with the person may think it's like an extension of their arm, and they can potentially feed themselves wherever they go. So in addition, we instrumented this arm with some sensors that we developed. So we use visual and haptic sensors, as I have said before as well. We use haptic sensors to make sure that we are applying the right kind of forces for different food items, as well as for safety, so that the robot doesn't poke a person too hard when they're feeding, right? It needs to be safe. The visual modality we use to detect food items, as well as to detect face, to detect mouth opening. And we use this thing called visual servoing. What that means is, even while feeding, if the person moves, the robot can track the person's movement and then bring the food near the person's mouth. So having said all this, the next thing is to actually use an algorithm to figure out, okay, how to pick up the food item so that I can actually pick it up and feed someone. And again, I am not going to go into the technical depth of it, but I'm just going to show you the architecture. This is how our algorithm looks like. The input is an image of the plate, okay? Then we have the first network, which is the retina net, which says, given this input image, it gives out the bounding boxes around every food item. Now, after that, we have a next hierarchical network called a skewering position action network, or SPANet, that we developed in our lab. What it does is it takes each of these food items and then outputs the probability of success for each action that the robot can take on that food item. And we decide the action spaces based on the taxonomy that we learned from the human data. So, but that's not the entire story, because, and we also add an extra environment classifier that is added as a one-hot encoding vector. What does this mean? It means that this network, to decide which action is the most successful, not only looks at the food item itself, which is from the bounding box, but also looks at its surroundings. So for example, the best strategy to pick up a carrot when it is isolated versus when it is near a wall or when it is stacked on top of other items like a lettuce salad or something like that is different. So the algorithm takes into this account, then to take this into account, and then figures out what is the best strategy to pick up the food item. So here is a little bit deeper idea of this architecture, where basically it's an AlexNet style architecture followed by convolution layers. And the environment classifier that I mentioned, it's added just before the final linear layer as a one-hot encoded vector. So here is a video. And here you see that the robot can pick up items not only in an isolated state, but also in a cluttered plate like on the left side. And the interesting thing is it can even generalize to some unseen food items. So as you can see here, the robot picked up this bell pepper without knowing that it's actually a bell pepper. It knows that it's a food item, as you can see from the labels on the inset picture on the left, right? So it could generalize. But the question is, these are what, like some 16 or 17 food items? But food is diverse. Like in a normal grocery store, there are like around in the order of like 40,000 different food items. How can we make sure that the robot can pick up all of these food items? And it's also very difficult to model, as I mentioned before. It's very difficult to have a simulator that can model all of these topological changes. Like, as you can see, when you pick up a pizza or the pasta or spaghetti, right? So how is it possible to even use this network and train it in all these different food items? It's not realistic and not scalable, right? So the idea is that robot needs to be able to adapt online if it sees a new item. For example, say I bring the robot to a person's home and I tell them, hey, please use this robot to feed yourself. And the person suddenly one day eats a new item that the robot doesn't know. How will the robot adapt to feed the person? So to use that idea, we use the idea of online learning, where the idea is you observe a state, and then you choose the action, again from the set of actions that we got from the taxonomy. And then we observe the reward. The reward can be whether the food is successfully on the fork or not, whether the robot was successfully able to pick up the food or not. And then based on this reward, we update our policy, right? And so now online learning is just a framework, but to be able to actually execute it, you need to model the problem. So we model this problem as a contextual bandit. I don't know if you guys are familiar with this term, but basically, so you may be familiar with this term called multi-arm bandits. And what that is basically you can think of this as going to a casino, and where you pull an arm, you pull a lever, right? And you get a reward. So you take an action, you get a reward. And there is this exploration-exploitation trade-off where you decide, should I keep pulling this one arm, or I explore new arms? That's a normal multi-arm bandit. What a contextual bandit is that it gives you an additional information, which is its context. So it's like once I look at the state, I pull the arm, and then I get the reward. So the state information or a context information is embedded there. But then the question is, how is it different from RL? Well, you can think of contextual bandits as a real-time, as a simplified version of RL, where in contextual bandits, you get the reward immediately after you take an action. But in an RL, it is possible to get the rewards at the end of an episode as well, right? With multiple time steps. The reason contextual bandits are very popular and hot topics right now is because of the sample complexity. And it's easier. If you want to translate something from simulation world to a real world where collecting data is hard, this is a more realistic model. And it fits well for our work, because for every action I take, I get the reward immediately. So the framework fits perfectly. So this is basically how our framework looks like. You have a context, and then remember the network that we talked about, SPANet before? We use SPANet as a featureizer to get the context from from the image, which is basically the last linear layer. And then we sample an action from that context using some exploration strategy. And then we take that action in the real world. For example, here the robot is trying to skewer a banana, and we get the reward. Is the banana on the fork or not? And based on that, we update it. And the idea is to minimize this cumulative regret that happens from the start till the current point of time. So these exploration strategies, like how do you sample actions from these contexts? One option is a traditional epsilon greedy, where the idea is with a probability epsilon, you, excuse me, excuse me, I am getting a call. Right. So now, so epsilon greedy, where with probability epsilon, you try a new action, but with 1 minus epsilon probability, you try the best action that you have seen. It's a traditional algorithm, right? But in addition, we tried this algorithm called a linear upper confidence bound, where the idea is you don't just look at the expectation of the rewards, but also the upper confidence bound. What this means is basically what it's doing is it basically gives us more chances for exploration, but while sacrificing the learning speed. So we tried both of these, and because this gives us more chances of exploration, this worked slightly better in our case. So here is an example of how this robot figures out online how to pick up something, right? So on the left, this basically what we added here to our framework that you see. The top framework is what we used before, right? You have an object detector, LatinaNet, we pass it to SPANet, and then it detects an action. All we have done is we have added a feedback loop where we sample an action, we observe the reward, and we update the policy. So let's look at this video. The current action to pick up the banana is the red graph. But you see when it starts, it starts with very low probability. But as it explores, its confidence on that correct action goes up. And after some trials, it figures out how to pick up the banana, even though it has never seen banana before. But while learning it, it does not forget other items that it has learned before. And from next time, it remembers how to pick up the banana. So the first time you give a new item, it may take multiple tries, but from next time, it immediately can pick up the same item with consistency. So this was very promising for us. And we thought, okay, we have reached a stage where we can actually start evaluating this system with actual people, right? And so
a quick question about the
yes.
The variants.
Yes.
Like how does the how are the manipulation strategies varied? Like what does it just change its angle, the force it's using?
Yeah, that's a great question. Basically, if you remember the taxonomy, in the taxonomy, we have a set of discrete actions. So we just took those actions and then we explored some of these actions. So basically, like say in our taxonomy, we had vertical skewering. We had vertical skewering with a different role. We had tilted skewering and all of these actions. So basically in this particular experiment, we had 6 actions, discrete high-level actions. And then the robot explores those and decides, okay, I need to vertically skewer, or I need to tilt skewer, or I need to rotate my arm and skewer. So it circles between these 6 actions.
So why did you guys decide to go with those 6 actions instead of varying along like an axis of different angles, like basically an axis of all the different metrics you guys could have varied?
As I mentioned, this was something that we learned from human data. So when we collected human data, the taxonomy that we developed, we found that these, and when we clustered the data of actual people feeding themselves, we found that their actions can be discretized across these various clusters. And so we use these different discrete clusters. Now the question is, we thought, okay, yes, the humans do that, but why didn't we use, instead of 6 actions, 50 actions or 100 actions with continuously varying these angles? The reason is, first, the sample complexity. Again, it's a real world application. And so collecting data, imagine you have to circle through 50 different actions when you actually try to learn a new food item. How long will it take for you to converge to the correct strategy? A person cannot keep waiting to be fed while the robot figures out what is the correct strategy to use, right? That's the first reason. Second reason, we found that they are actually not that significant. So for example, say I have a vertical skewering at 0 angles, and then I say I keep the angle, changing the angle 5 degrees, 10 degrees, 15 degrees, 20 degrees, 30 degrees, like that till 90 degrees. We found that there is no significant difference between 0-degree vertical skewering and 5-degree vertical skewering when it comes to actually skewering the food item. So like this, like even if continuous action spaces can be very useful for some other applications, but for this particular task that we are doing, it was not that informative. Hope that answers your question.
Yeah, great answer. And then another question about the generalization from earlier.
Okay.
So is it, so when I was figuring out how to pick the bell pepper for the first time, was it was it kind of looking at the bell pepper and associating it with similar looking objects to pick the strategy, or?
Yes, absolutely. Very, very good, very keen observation. That is exactly what is happening. Basically, what we found out when we tried to see that, okay, how does it know how to generalize? What we found out is generalizing across shapes and sizes. So for example, if the robot has seen how to pick up a carrot, it would know how to pick up a celery. Or if the robot knows how to pick up a spinach leaf, it would know how to pick up a lettuce leaf or something else. So it uses those features like the shape and size features to be able to generalize. Great question. Great question.
And then following up on that, like you can imagine two kinds of food objects that look very similar but require different strategies.
Yeah.
I can't think of an example right now, but
no, that you are absolutely right. And that's why currently we are working on going, again, as I said, this particular thing was just using vision, right?
Yeah.
But like, for example, I can have a white food item, I don't know what, maybe a marshmallow or something in the same shape as a banana, and they are both, but they may require very different strategies, right?
Yeah.
And so that's where what we are trying to do now is add haptics into this mix. And so we have just gotten some very promising results where we found that for those kind of confusing cases, which can confuse vision, if you add also the force modality, force information data from skewering, you can tell the differences even if they are visually similar. And you can basically like model some of those texture differences or softness and hardness and things like that.
Yeah, but I bet that's kind of tricky because the robot arm, by the time it's able to detect the force, it's already in a certain position. So if the strategy involves,
there are multiple ways of dealing with it. There is this thing called post hoc contexts. What that means is even if one context is a little bit delayed than the first context. So for example, the visual context comes earlier and the haptic context comes later when it's actually interacting with the food. If you remember when I showed originally, it can find out within 0.7 seconds on average what food, like what category of food item it is. So if that is the case, once it knows within 0.7 seconds, it can adapt its strategy using this delayed context. So say, for example, I was thinking that I would have to pick up this particular object by going vertically. And so I went vertically. But now when I went and I skewered it, I figured out, oh, this looks like a banana. And so if I just lift it off, it may fall off. So after skewering also, once I realize that it's a banana, I can, instead of lifting it up directly, I can scoop it up. So there are ways to be able to recover using these delayed contexts. Another approach to be able to do this is that, okay, you just assume that first time it failed. That's okay. But next time, because it has already the interaction data, now you can combine both of this so that in the second try, it can pick it up. So there are multiple ways of going at it, and we are looking at multiple approaches.
Thanks. It was a great answer.
Thank you. Okay. So now coming back to the original question, tying it back to the original motivation, right? Okay, this is great. We have developed these algorithms. It can do different things, but is it actually going to help people? Are people actually going to use it? So first we thought, let's see, this is not the first feeding device that exists, right? There are some commercial feeding devices. For example, OB is a popular one. How does our system compare to this OB device? And to be able to do that, this OB device does not have any intelligence. So it is mounted on the table and it's completely teleoperated, right? So to be able to do that, the first thing to understand, and this goes for any kind of system that we are building, whether it's a robotic system, any assistive system, or anything that we do, the question is to figure out what is the right metric to use to evaluate this. And to figure that out, we talk to all the stakeholders and like caregivers, care recipients, occupational therapists who have been feeding people for 40 years, and all of these people. and experts basically. And we found that robot-assisted feeding is not just about picking up the food and feeding someone. That's just providing the functionality, which is a simple nourishment. It's much more. It has complex social, cultural, and self-identity implications, because a meal is much more than just bringing the food to someone's mouth. And so we developed this contextual framework where we looked at, we developed this, how we came up with this framework, like how an assistive technology like this should be able to, should be evaluated. So there are 6 things. You need to see whether it does the function that it's supposed to do, right? Technical function. Technology robustness. Can it adapt to uncertainties? Information gaps. Can it communicate with the users? Usability. Can it adapt to user preferences? What is the point of developing this in the lab if people do not use it in their real world? So social acceptance and system integration. How does it integrate with other systems around it? And so based on all this, we evaluated these 2 systems, and we found that especially our system was better than the OB system in terms of robustness, obviously because our system has intelligence and it can adapt to certain things, while OB has minimal intelligence. But OB is actually being used by real people with mobility limitations, and we have not done any study yet. So to cover up that gap, we thought, like, how do we make sure that our intended target population actually adopts this technology? So we developed this this robot. Basically, we did this study where the robot picked up different food items and fed someone, like all of these people with different mobility limitations. And it's very difficult to do this study because different people use different interfaces. Some people use head trackers. Some people use sip and puff devices. So we had to integrate our system to all of these different interfaces. And the interaction looks like this. We had multiple interfaces, but let's say the person is interacting with the robot with a voice interface. So the way they will interact with the robot will be like this. The person will sit on the wheelchair, and then the person will say, "Hey robot, feed me a strawberry," and that's it. And then the robot will go on top of the plate, look at where the strawberry is, and then use the algorithm to figure out how best to pick it up, bring it near the mouth, and feed the person. And then the next bite starts. So, but the question was, originally when I mentioned that we need more autonomy, is it always true? And so for that, we made different levels of autonomy in the system. And we asked people to be fed using all these different versions randomly. They don't know, like, basically which will come after what. And we asked them to rate. In addition, we deliberately introduced errors because the idea was that with autonomy in real world, there will be errors, right? So are they tolerant to these errors? And so what we found was very interesting. We found that people people with higher mobility limitations, like people with C1, C2, who barely can move their head a little bit, they were very highly forgiving of the robots. Even if the robot did errors, they said they will use it. But people who had less mobility limitations, they had higher expectations of the robot. So they said, for them, like people with C6, C7 injury, that if the robot fails even 20% of the time, they will not use it. So the acceptance depends on the user's conditions, and we need to adapt the system to the particular user. But overall, people loved it. As you can see from one of the comments here, which is written, "The technology allows me to do more things on my own. Of course, giving me more independence and making me feel more free, and gives me something to look forward to." So to conclude, assistive feeding is a high impact, technically challenging task where byte acquisition and byte transfer are both challenging, and we can benefit from flexibility in the system to account for all these different user preferences, because we learned that every user is different. And so basically through this presentation, we have seen that how we can infer properties and how we can leverage these properties to actually perform an activity of daily living. Here are some open data sets that you can use to be able to do different, like to try out different algorithms and see how well you do. We would love to get you involved. And here are some of the other projects that we have done, where I have also looked at other modalities like active thermography, combining the tactile sensing with vision, as well as helping people in telesurgical and applications and things like that. So to conclude, feeding is just the beginning, but I want to extend the work to multiple activities of daily living. And my goal is to enable robots to assist people with mobility limitations with tasks of daily living. Thank you.
Wow. Thanks, Tapo. It was a really interesting, well-prepared talk.
Thank you. Thank you. Let me know if you have any questions. I'm happy to chat.
Yeah, for sure. Drew and Jason, you all can go first.
You can go ahead. Thanks,
Okay.
thanks for the talk, by the way.
Yeah, no worries. So one of the questions we got was, can you share a little bit about your background, what made you interested in robotics and specifically in mobility and robot-human interaction?
Yeah, that's a great question. So I would say in my undergrad, it was kind of like a serendipitous.
Yeah.
Of course, I like to, I used to play with Legos and stuff all the time, but it was more of just a hobby stuff, or like just a hobby thing. But like when I really started getting into research was kind of serendipitous. In my undergrad, which I did in India, during my final year, actually not final year, my junior year, I had to do a project. And so there you have to do a junior project as well as a senior project. And so in the junior project, a team formed where they wanted to look at some robotics project. And so they invited me and I said, okay, sure. And so we met with an advisor in our university, and the advisor said that how about you, like in India, as you know, cricket, the sport is very common, is very, very popular. So someone said, why don't you build a cricket playing robot? So I was like, that's very interesting. That was the kind of the introduction where basically the cricket playing robot there, I learned how to design a robot, including mechanical engineering. It needs mechanical engineering, everything, kinematics, dynamics, and all of these things. I learned how a robot can be made intelligent, which requires, some machine learning algorithms or some other things. I learned how to control the robot, where you need some control systems experience and some ECE experience. I learned how to solder a circuit. And so all of these things, and so robotics is very interdisciplinary. Whichever department, whichever discipline you come from, you can always contribute. And so based on that experience, I was like, wow, this is a very rich field. And after that, I never looked back. I did my senior project also in robotics. And then I went and did my master's in robotics. I worked a little bit in industry or in research organization in robotics. I did my PhD in robotics. I did my postdoc in robotics. And now I'm going to join faculty, where my lab is also going to be on robotics.
Super cool. And following on to that, how long did it take you to, let's go to the cricket robot project, for example. How long did it take you to ramp up, and what would you recommend people who are like beginners to the robotic field and how they should ramp up?
Yeah, that's an excellent question. So I have to say that the learning curve is steep, but it depends on what you want to do, right? A robotic system, of course, needs both everything. Needs design, needs electronics, needs algorithms, needs intelligence, all of these things, right? Well, by needs, I mean, it can benefit by having. It doesn't really, it depends on the application. But so ideally, the best way to ramp up is, what I felt from my experience is to have a form, basically create an interdisciplinary group where people from different departments, even other departments like social sciences, psychology, like everything, because human-robot interaction also is inspired from all of these things. So you form an interdisciplinary team where different people do different things. Your role is a particularly one part of the robotic system, but you also see what other people are doing. And by interacting with people from your peers, you learn what to do. Having said that, I don't know what departments you guys are from, but if you are from computer science, I can specifically say, especially in robotics and also in mechanical engineering, two things can be really useful. First is knowledge of linear algebra and probability and statistics. These two things go a long way. Most of these things that you see, either probabilistic approaches, or if it's even a kinematics, dynamics, or even other things, it's linear algebra. So make sure that your fundamentals are strong in linear algebra and probability and statistics. And regardless of what department you come from, whether you have courses on that or not, it is always a good idea to train yourself with coding, like code all the time. If you do these two things, you are already set. Everything else will just follow.
It's great advice. Thanks, Tapo. And then kind of related to that, so how full stack is the team at the Personal Robotics Lab? Do they make their own hardware? How much is outsourced? Stuff like that.
Yeah. So basically, we have, like, I am a full stack roboticist, and our lab is also a very full stack robot lab. We have people from computer science, from electrical engineering, from mechanical engineering, even from there is a department here, right, called human-centered design engineering or something like that. So HCDE. So there are different people from all these different departments that they are actually our lab members. So for example, in this particular project, of course, we have developed algorithms, but we have also developed controllers. We have, like, the sensors that you saw. We use mechanical engineering expertise to actually manufacture those sensors using the makerspace, as well as like 3D prototyping, as well as the mechanical engineering labs. We used electronics expertise to design our own circuits to be able to do some of those things as well. So our lab especially is very full stack. Having said that, there are other robotics labs which are not as full stack as ours, where they focus on just one aspect. As I said, robotics is interdisciplinary, and you can choose to focus on one aspect or the other. So for them, they cover up for the other aspects. For example, a lab which just focuses on algorithms, for example, they would just buy a robot or buy sensors or do something or consult or outsource this, get those things done, and they will just focus on this. So it's possible to do multiple things, but a true roboticist, I would say, needs to get hands-on, and that's where a knowledge on all of these things, a little bit knowledge on all of these things can really help.
Going on to the HCDE aspect of things,
yeah.
So what kind of challenges are there in terms of the design space, like in terms of maybe the form factor, how the robot looks, stuff like that?
Yeah, it's an excellent question. Actually, related to that, I think I missed asking one of the earlier questions, one earlier part of the questions when you asked not just robotics, but how did I get interested in HRI? Basically, right. Through that project, the first project, the junior project, it did not have any human-robot interaction component. But later on, in my master's, I did a project where I did a human-robot interaction problem. And that's where I was like, okay, I need to work with people. And then, you know, there is this saying, it's not my own saying, but I love it. They ask, there's this saying which says, someone asks, you know, what is the hardest problem in computer science? And people say humans. Because modeling humans are so dynamic, ever-changing things that modeling humans is so interesting. And if a robot were to work with the humans, they have to infer the human intent or figure out the things like that. And so it's also a very technically challenging at the same time very interesting problems. So that's how I got interested. Now coming back to your, sorry for digressing, coming back to your current question. So basically HCD, like the design space is very interesting. Form factor is very interesting. Like think about it. If we are especially interested in taking the robot from lab to the real world, which is my goal, you don't want to use a humongous robot in your home, right? So form factors matter. And so choice of hardware matters as well. But HCD has much bigger role to play, not in addition to just the form factor of the robot. For example, say the interface. For example, the interfaces that we designed, like for the people with mobility limitations to interact with it. Like think about UX designers, UI designers, right? Like you need to be able to develop an interface so that people who cannot use their fingers or like they are mobility limited, right? How can they use these interfaces to do the similar tasks that such as an able-bodied person? So you have to also design these intelligent interfaces that also gives this equivalent information to these people and make all these technologies accessible and inclusive. So that's why I think there are many roles that HCD engineers can play. And also, obviously, they play an integral role in doing like studies with humans where we want to evaluate it and see how things work. In fact, we actually have in computer science, not my particular lab, but our adjacent lab, this is called the Human-Centered Robotics Lab. They have a project, it's run by Maya Kakmak. She runs a project with a PI from, I think HCDE. Her name is Ellen Borlin. So they work on finding out using robots to address stress in teens. So these collaborations are very useful.
Yeah, that's really cool to hear about. I also was wondering in terms of specifically the look of the robot, like how much consideration goes into that?
Yeah, that's an excellent question. A lot, I would say a lot. So for example, but it depends on the application. So say, so there is this thing in the literature called uncanny valley.
Yeah.
And what that means is, basically what it means is, okay, you can also tie it to this concept in social sciences called homophily. What it means is, if you have some traits that are common with the technology, you feel more connected to it, you trust the technology more, and that leads for you to use those robots for long term. And so people researchers sometimes try to make these robots look like entities that we are familiar with. So for example, a dog, like the Aibo dog, or humanoids or things like that. But we need to be very careful, because as you become more and more realistic, at some point of time, it is very realistic, but it is still not completely there. And that's where people say that you suddenly jump, because people start thinking of those appearances as creepy, because it's different enough that you do not immediately think it's a machine. But when you think of this as a human or something that you're really familiar with, there are subtle differences that make it very weird. And so you need to be very careful that the appearances that you do not go into that kind of range. And this is a continuous kind of, how do I say this, a consideration for design engineers. Our application is very functionally focused, and so it's just an arm. So that thing is not so much applicable for us, but it is more for some of the social robotics applications where you have humanoids or dogs doing some therapy sessions or just interacting with people, that kind of thing.
Yeah, this is a great answer, and the uncanny valley is a great point.
Yeah.
One thing that,
yeah.
Oh, sorry, continue.
Oh, no. I mean, you please continue with your questions. I mean, my responses were just that.
Sure. Yeah. So going off of the look of the arm, I was just wondering, how open was the design space? Were you just thinking of just arms, or were there any other ways of, like, for example, this is just a naive idea I had, but like maybe a drone, because a drone could fly around more.
Right. That's a good question. The thing is, we were mostly thinking of indoor spaces, like in a person's dining room, or feeding there. And so there, using drones may be challenging. Also, in fact, think about it, right? Having a drone to come pick up a food from a plate and bring it near a mouth, it's just not like, it's just the interactions. There are so many problems with it. Like, are you even okay with a drone having a food and coming near your mouth and feeding you? If you think of an arm, you can think of this as an extension of your arm automatically, right? An arm, and you can do this. So arm was an obvious choice for us. Having said that, you raised an interesting point, which is, instead of an arm mounted on a wheelchair, you could always use another robot that is not mounted on a wheelchair, like a mobile platform with an arm, like a fetch robot or other robots, and if by the way, one thing I wanted to definitely tell you at this point, that if any of you guys are interested to come visit our lab, please let me know. Of course, once our labs reopen, I'd be happy to invite you and show you the different robots that we have in our lab. So you will see when you come that there are different mobile manipulators, and so there, if you like, you could use those robots, and yes, you could. But the reason we went with a wheelchair-mounted robot, as I mentioned in my presentation, was mainly because we wanted the robot to move with the person, so that the person can eat wherever they want. It doesn't have to be fixed to a particular table. They can go wherever they want. And the arm can be used not just for feeding. It can be used to pick up a book, to pick up a water bottle, and things like that. So the arm, it's like an extension of their body. So it moves with their body. That's why we chose this platform.
Right. No, I totally agree with you. Like having it attached to the wheelchair, that's a thing that I think is a great point. I think it was more of like, in terms of like manipulators, let's say there's like a universe of manipulators. Is the arm the optimum, or is there like a greater optimum? And I know you're also optimizing for like user friendliness and people like that. So the arm could satisfy manipulation and user friendliness. But let's say you're judging along those two axes, like is an arm the optimum, or is there like a higher?
Yeah, that's a great question. I think it's a very application dependent answer, because there is no universal solution to every kind of application. Even within arms, an arm can have 6 degrees of freedom, or 7 degrees of freedom, or 3 degrees of freedom, or 2 degrees of freedom. So it totally depends on the application. For our application, this arm with the 2 degrees of freedom gripper was adequate. But say if you want to do in-hand manipulation, where you have an object, say I have this, and I want to do this kind of manipulation. With 2 fingers, without using the environment, it may become difficult, like 2 parallel jaw grippers. So I may have to change the gripper design. Or for example, say I have another situation where I want to, for example, say snake around a very cluttered environment, as I showed in one of the videos. There, you may want more joints so that the robot can have actually snake around instead of having just those 6 degrees of freedom, right? So it totally depends on the application, and it's not just arms. There can always be a question: do you want 1 arm or 2 arms? Do you even don't want arms? Do you want wheels, like a mobile manipulator? Do you want legs instead of wheels? All of these things, there is no universal answer. It totally depends on what you want to do.
Yeah, great point. And then also that is related to my next question, which is about utensils specifically. So for picking utensils, did you guys go with forks because those were the ones that were like universally available, or could you have designed like your own, like custom?
Yeah, excellent question. Excellent question. And trust me, I always get this this question asked. Basically, yes. For your, it's basically because of your first thing, which is we wanted someone to just get the robot and use the utensils that they have to be able to do whatever they want, and not have other accessories that they need to buy with the robot to be able to do these things. Having said that, I am totally open to the idea of designing a tool that works with many different food items. In fact, we started looking at sporks, and I have a spork somewhere here in my table here. But we found that at least with spork, it's like jack of all trades, master of none. Like it can pick up some liquids, it can pick up some solid, but it's not great at all the things that a metallic fork could do, or a complete spoon could do. So we need to be able to carefully design those tools. But if someone designs it, or if we look at it in future, and if we see some promise, I'm definitely open to using it. We just haven't looked at that yet.
For sure. And then on the material science front, is there any like R&D work done on like material science kind of stuff, like maybe a more flexible arm, like instead of having joints? Like I don't know how snakes move exactly. Do they use joints? or maybe
So
like how a worm moves?
you can have, again, multiple designs.
Yeah.
You can have many different joints and have them actuate, or you can have a continuous thing like an earthworm, for example.
Yeah.
So coming to that, yes, you are absolutely right. There is this new field of robotics that has become really, really hot right now. It's called soft robotics. And what they are doing is exactly looking at that. But basically, material scientists are developing these new materials every day that that you can use. So instead of having rigid links, you can have a continuous arm with infinite degrees of freedom. And then it can actually truly snake around instead of having like many joints. And so the soft robotics is very hot area right now, and people and the applications are basically all of these applications that I mentioned, as well as interacting with humans. Because imagine if an arm is soft, it will inherently be safe, right? Because it will not impact the person with a lot of force. So it's a nascent field. It's a new field, right? There is promise, but there are lots of things that still need to be solved, because if you think again, going soft, so a rigid arm can pick up this heavy bottle easily. A soft arm may not be able to pick it up because of its weight. So there are many trade-offs, and material scientists are playing a huge role in coming up with solutions that roboticists can use. Actually, a side point, even some material science things are important in our work. So again, I did not go into the deep, but one of the sensors that we're using, the tactile sensor, which is mounted on the fingertip of the robot that we developed in our lab, is based on gel. That's a function of silicone and basically a solvent and silicone gel. We create the silicone gel using a very specific kind of a proportion. I forgot what the proportion is from the top of my head. So there also material science comes in, because depending on the compliance of the gel, we can sense different ranges of forces.
Yeah, soft robotics is super cool. So I'm glad that you brought that up.
Yeah.
One thing I also wanted to ask was, let's say that like tomorrow, or let's say that somehow we go to a world where there's another solution to this problem. Like, sorry about my dog, but
Yeah,
like, let's say there's a BCI with an exoskeleton, so that these people are now able to walk around and like able to help, like, without the use of a robotic assistant. What kind of other tasks could a technology like this be used for?
Yeah. So you're talking about BCIs, right?
I was talking, so BCIs was a part of it, but like, I think specifically I was saying, like, let's say that this problem is solved in another way. Let's say that there's really good stem cells or exoskeletons or something.
I see. So there are multiple ways of doing it, right? So let me focus on this. Assistive robotics. I work on assistive robotics. So what it does is using robots to enable people to do these tasks. It doesn't, if the person has spinal cord injury before using the robot, after using the robot also the person still has spinal cord injury. It doesn't change anything in the person. It just adds an extra helper to the person so that the person can actually do the task with the existing limitation, mobility limitation. Having said that, there is another branch of engineering called rehabilitation engineering. Rehabilitation engineering, what they look at is they want to say, yes, assistance is great, but we also want to rehabilitate the person so that the person's functionalities start improving. So for example, today, the person couldn't pick up the fork and bring it to the mouth. They could probably move it just 1 inch. After continuous rehab therapies, maybe after 6 months, they can move the robot, move the fork 2 inches or 3 inches. So the rehabilitation looks at exactly those things, where you do different experiments. You look at EMGs to see how your muscles, generate these signals and everything. And you basically using feedback, you try to even do artificial stimulation of your muscles and see, can you make the person regain some of these functionalities. Now, there is even another part where they are saying that, okay, I am not going to rehabilitate the person. I may, but I may not. But I may not also have an artificial entity outside my body to help this person, like in assistive robotics. But what I will do is I'll have like an exoskeleton or something like that. So what exoskeleton does is it says, okay, you are going to use your arm to pick up, but you cannot move it. So now my exoskeleton technology will give it more power so that you can actually move it. So you are actually using your arm to do the task instead of relying on a robot, a separate robot. But you are also not increasing the functionality. Exoskeletons can be used in an active mode to train people to rehabilitate as well. But the other side is you just use it to do the function instead of making some changes. And finally, especially for people who are amputees, for example, you can also add artificial limbs, whether legs or arms. And this is the branch of prosthetics. And using that, you can also do these assistants. So there are different branches looking at different ways of solving the same problem.
For sure. Well, I think my question was more of like assuming that this is solved in another way. It's mostly just like what uses, what could this tool be used for beyond just accessibility?
You mean our algorithms? Can you?
Yeah, I'll elaborate. So for example, the robot arm or the algorithms, like what other use cases are there?
Oh, okay, that's a different question. Yes. Algorithms that we have developed, for example, the algorithm that tells us what is the best strategy to use to pick up a food item, it can potentially be used for any kind of grasping applications, right? In manufacturing, where the robot goes and needs to grasp something, and you have different grasping candidates, and the robot needs to say, what is the probability of successfully picking up this screw or something like that? What action should I take so that it gives the maximum success probability? But there needs to be some changes, right? First, the context will change. So what is the input that comes to the algorithm? The action spaces will change. Instead of a fork and having those actions that we saw from the taxonomy by studying humans, you will have a different set of actions that are relevant to the task that you are doing. And of course, you may have to retrain the network for that particular task. But the algorithm structure itself, or for example, the idea of using online learning, using contextual bandits and those kind of things should be transferable to different things, provided you make those adjustments in their action spaces, how rewards are seen, and the contexts.
Yeah, thanks for that answer. One thing I wanted to ask about was the reinforcement learning part. So I think you mentioned, could you go over what the reward function was again?
Yeah, so the reward is, in our case, the contextual bandit case, the reward is just binary. Whether you were successfully able to pick up the food or you were not successfully able to pick up the food. And so the way we find that out is, so the robot skewers it and goes and lifts up, right? And when it lifts up, you can tell whether the food item is on the fork or not, using both vision as well as haptics. If the weight of the fork changes, that means there is food there. Or using vision, you can say if there is a lump of food near the fork tip. So using this, you can tell whether the robot was successfully able to pick up the food item or not. And so that's how we do the reward. So it's a binary reward, and then based on that, we update the policy.
Sure. So if it's a binary reward, what if it picked up the wrong food item?
Yeah, that's an excellent question. Here we do not consider that in this particular thing, but you can easily extend the formalism that we have to those kind of things as well. Basically, we can just say that now it's still success and failure, but maybe we can have different kinds of failures, and we can have a reward instead of just 2 numbers, but 3 or 4 different numbers.
Yeah.
Good question.
Thanks. So right now the pipeline is split between identifying the food object and then figuring out a strategy. Is there a way to further simplify the pipeline and use more automation, maybe using some other kind of artificial intelligence techniques?
Can you elaborate? Because everything is automated there, right?
Right.
It's just modular. Do you mean end-to-end systems?
Yeah, I think end-to-end is a better description.
Okay. So yeah. So again, everything that I've shown in the pipeline is automated. Everything is autonomous. But
Right.
yes, we chose modular because again, with end-to-end systems, like say from image to direct robot motions, they in real world with these sophisticated tasks with intricate manipulation, they require that their sample complexity is huge. You require a lot of data and you do not really know what works and what doesn't. So that's why for these kind of real world applications with intricate manipulation, subtle manipulation strategies, where the penalty of the reward is huge, penalty of a wrong action is huge, and we have restrictions in that number of data that we can collect, we separated this system into different modular categories where each of these modular categories are autonomous and the connection is also autonomous, but it's not end-to-end. And this also helps us better understand the failure modes. For example, if the failure mode is in the perception object detection, I know where to focus on. If the failure mode is on the planning, I know where to focus on. If the failure mode is in selecting the right strategy, I know where to focus on instead of a one big system that takes end-to-end. Does that make sense?
Yeah, that's a great point. And I really like how for this answer, and I think an earlier answer as well, you mentioned how certain strategies don't really work that well in your specific use case because it has to be fast and it has to happen in the real world. It's always cool to hear about. The next question I got was the question about machine learning.
Okay.
So they asked, how much of the work is purely machine learning and related code versus experimentation with different hardware components, modifications, or like how much like algorithmic thinking is involved versus just feeding data into some model?
A lot. So for example, like for example, the RetinaNet part. The RetinaNet part is off the shelf. We just retrained it with our food data, right? The RetinaNet was pre-trained on ImageNet, and so the object detection part, the RetinaNet is pre-trained, but is pre-trained on ImageNet, and we just retrain it with the data. But like the SPANet, where the skewing position action network, we design our of course, inspired by some other architectures. It of course has these different building blocks like convolution layers, linear layers, things like that. But we build our own architecture, and it's not just that. We also figured out, for example, how to take in the environmental information, the surrounding environment information, and where to feed it and things like that. So that's the algorithmic part. That's like, for example, the one part, right? Second thing, like for example, the contextual bandits. Contextual bandits part is also it's very algorithmic because for now the part that I'm not showing you here, where you combine these delayed contexts that I talked about, the postdoc contexts. Right now, in the contextual bandit formalism, there is no work that looks at how the regret bound of these algorithms change when you apply this delayed context, and how can you combine these delayed contexts. Is there a theoretical guarantee that you can say that adding a delayed context, regardless of how good or bad the context is, will it actually make the performance worse or better, or will it at least have the same performance as the original context? Those theoretical things and everything is again requires a lot of theoretical algorithmic thinking. Having said that, robotics, especially, I am particularly excited in real world applications. So whenever we develop an algorithm, it is useless for us if it is not actually useful in the real world. And so we always challenge ourselves and ask ourselves, whatever we are developing, is it actually going to be useful? So there are different ways of looking at research, right? But our lab in general, and I, of course, look at from this point of view. I identify a problem, and then I try to develop techniques that solve the problem. But many people, what they do is and this is what I really like, because I'm a very real world focused, a problem focused person. And this is my research philosophy. But many people, what they do is they want to develop a new theoretical algorithm or a new thing. And we will develop new theory as well, as I told you just now, if it is needed by the problem. But many people do the other way, where you develop the theory because you see that there is a scope of doing something novel there. And it's very interesting. It's an interesting theoretical contribution. But then to show whether it works or not, you try to find problems where you actually see the difference. And in our lab, we also have some work like that, but we found that if we are not carefully thinking about how we are developing these things, it may come up that in any real world applications that really matters, that happens in the real world, maybe the algorithm that you developed, it's a good intellectual exercise, but it is not really useful in having an impact in the society. And so to actually show that that algorithm works, you need to create a very engineered condition, either in simulation or in the real world, to actually show, oh, it works with better than baseline for 2% of the time. And definitely some labs do that, but that's not my research philosophy.
Sure. It's a very interesting point about how your lab is more customer facing. I think theory can certainly be useful, right? Like Einstein came up with relativity, and at the time, I don't know if people really used it for much, but now it's like the basis for computers and communication.
Absolutely, absolutely. And as I said, there are these two approaches, and people do these approaches. It's just that I am very problem focused, because the whole point of, I think of robotics as a way to help people, and it's a very applied field. And and a roboticist who uses machine learning is different from a machine learning researcher. And so I am a core roboticist, full stack roboticist. And I am happy to develop theory that helps in solving some problem, or I'm happy to, find out ways or technologies that is happy to, that solves a particular problem. But the way you define yourself is slightly different. And again, all of these things are just different sorts of different impact that you have. And a person, even if you do not find a problem, a theory problem, even if you do not find an application now, 50 years down the line or 100 years down the line, it can be a game-changing thing. Exactly. And that's amazing. And that's and I'm totally fine with that. It's just that my research philosophy as a roboticist is a little different. That's how I focus on.
That totally makes sense. One thing I wanted to ask about from earlier was so you said for SPANet, you guys are choosing between 6 different strategies. How do you know that the 6 different strategies are representative of maybe not all food types, but a significant majority? Yeah. And like the data set you trained on, how did you make sure it was representative?
Yeah, that's an excellent question. Basically, it's a very data dependent thing, and I cannot claim that this is a full taxonomy. In fact, the paper that we published, we actually say that it's a partial taxonomy, because the actions that we saw are only based on the food items that we gave the human, right? Yeah. And it is not possible to give them every food item that exists. But having said that, when we chose those food items, we tried to vary them across different scales, sizes, shapes, textures, softness, homogeneity versus heterogeneity, and things like that. But yes, definitely this is a partial taxonomy, and there is no way to guarantee that this covers all the strategies that people use. Yeah.
For sure. Do you have an estimate on the size of the taxonomy that represents like human strategies across all?
That's a very difficult question, Saket. I really don't know. We'll probably, it's a huge research question. It's an open research question. It's something that would be very interesting to look at. But at this point, it's very difficult for me to estimate something.
For sure. So far, those 6 strategies that you found have been working well on most of the food types that have been tested, right?
Yes, that's true. That's for true. So far, again, as I said, with the kind of food items that we have tested, we haven't had the need to augment the space of like action space. But I know that when we go to more varied food items, we may have to look at that. And we are actually, in fact, we have a couple of undergrads in my team who are looking at transferring from discrete action spaces to continuous action spaces, as you pointed out.
Nice. That's pretty cool. So after food manipulation, what other use cases have been worked on for this tool specifically, or in development?
What do you mean by tools here?
Oh, I think you might have misheard. I think I said, so for ADA, the robotic arm,
Oh,
Like
the
you mentioned-
ADA, the arm. Okay.
Yeah, so you mentioned you wanted to use it for not just feeding, but many other tasks. I was wondering which of those tasks you're currently working on, if you can share.
Oh yeah, sure. So right now, of course, in this lab, in this particular lab where I'm a postdoc, I'm leading the assistive feeding project. And this project itself is so rich that I can keep continuing to work on this for 20 years. But having said that, yeah, it's huge, right? I mean, it's huge. I mean, look at how you eat pasta or how you eat a Chipotle bowl. It's amazing the strategies that you use. Like it's amazing. Like look at, like imagine, like I have fed one person, but imagine the interesting social dynamics when you feed a person with their family members. So social dining scenario. How do you know when to feed the person? The person may be talking to someone, maybe doing something else. It's a very, very interesting question. Or for example, how do you adapt the robot to user preferences? Like, for example, the person may say, oh, today I don't like strawberry. Tomorrow I may like strawberry. Or I like this much amount of food in my mouth in one bite. And all of these things. All of these things, however subtle they may be, they become very important when you try to translate this technology to the real world for long-term usage. Otherwise, someone will not use. They will say, they will say, like, it's not doing what I want it to do. So the robot needs to adapt to user preferences. The robot needs to look at all of these interesting interpersonal dynamics that happens in social, like human-robot interaction, human-robot group collaboration. The robot needs to figure out how to manipulate all of these different food items with different physical characteristics, right? And so these research challenges are like 20 years down the line. If I see that I can solve all these things, I will be so proud of myself. Yeah. Having said that, I can also say that I am in general interested in looking at going beyond feeding to other activities of daily living. For example, dressing someone, or for example, assisting someone with instrumental activities of daily living, ideals. For example, things like meal preparation. Like right now, we are assuming that someone is preparing the meal and putting it on the table, right? Then the robot feeds. But what about the previous step, meal preparation? What about many other aspects? For example, cleaning, helping person with something else like laundry, like all kinds of housework. These are all instrumental activities of daily living. So there is a range of tasks. And again, in my lab at Cornell, this is not the only robot that's going to be there. Depending on the task, as I mentioned, I may need a mobile manipulator. I may need something else. And so we'll have multiple robot platforms looking at different problems. But in general, they span the research fields of robot manipulation, touch perception or haptic perception, and human-robot interaction. And these fields are far from being solved. We are just scratching the surface of this. Actually, at this point, I would also like to say, I don't know how many people will see this recording, but I will be, if anybody is interested in these kinds of work and they want to work with me, please email me, because I will be looking for students from next fall when I join Cornell. Yeah.
Yeah, I'll make sure that your email is included when the recording gets uploaded.
Thank you.
Yeah.
Yeah. So basically, it's a very rich field, Saket. It's a very rich field.
For sure. And then on the topic of difficulty, do you think that this task of feeding, like obviously there's no way to know, but do you think it's an AI complete problem?
This is just, it's just I don't want to, I need to be careful about what I comment, because
yeah,
it's just there are so many factors right now. I can only say that there is promise and there is development happening, and down the line we'll be able to solve different challenges. But at this point, it's not even clear if we want AI to make this system completely autonomous. Because as I said, I don't know if you could catch this, but in the last part of my presentation, when we did the study, we actually found that some people actually want more control of the robot. They want to tell the robot what to do instead of just saying, feed me a strawberry and let the robot do everything. So
but that level of autonomy, sorry to interrupt, but that level of autonomy is kind of a hyperparameter that can also be
Yeah.
learned by the system.
Yes, yes, exactly. And that's another level of I would say um, like a usability, like a learning from user preferences. Exactly.
Yeah.
But when you first bring the robot, just like when you explore different actions to figure out what is the right action, you have a set of actions, right, with you. You need to have a flexible system where you have this set of different autonomy levels built in, where the robot figures out what is the right autonomy setting for that particular person, right? And how to even represent this mathematically? It's a very interesting problem, right? And so it's just very difficult to say this, but I have hope, again, as I said, that the technology doesn't need to wait to solve all these problems to go a certain place. As with every technology, for example, think about Roomba. It is the most widely used robot in our homes, and by no means it does the job perfectly, but people still buy it. So the question is, we do not really need to wait for 20, even though research questions wise, it's a rich platform and I can keep working on this to solve all these problems. But I do not need to wait for 20 years to bring it to someone's home. If I clarify the expectations that this robot can only do this and cannot do something else, and then I bring it, introduce it in a person's home, then it's fine, as long as they are fine with this minimum set of capabilities that the robot currently has. And then over time, you can update, you can add more features to the robot, right? That's exactly what happens with even apps and things like that. So even though the research questions can go beyond like 5 years, 10 years, 20 years, to bring it to a real person's home for long-term use, it can happen much quicker. We need to clarify what are our top priorities to solve, and what are those minimum set of capabilities to have in the robot, so that the person would be willing to actually have it and use it to do their tasks in their homes.
So one interesting thing that you mentioned earlier was that the reward function isn't like, for example, what people want from it. Like they want varying levels of autonomy. So the reward function isn't just like if we were representing this problem that way, it isn't just like if the robot picks up the food or not.
Oh yeah, oh yeah. Right now, this problem that I showed you, as I mentioned, I just looked at byte acquisition.
Yeah.
But when it comes to the actual human-robot interaction of byte transfer, the question comes, it's very subjective. Like, was the byte comfortable to you? And then it's like your reward function is a combination of these objective metrics and subjective metrics. And again, the question comes, how do you represent these rewards? These are very interesting research questions. And in fact, I am currently looking at exactly this. So yeah, as I said, all of these sub-problems have more sub-problems, and it's just, yeah, it's just very interesting, rich field.
Are you looking at inverse reinforcement learning to kind of learn the reward function?
Yep. That is something that I've just recently started looking at, where we are saying that, instead of just using the human to find out, to create a taxonomy, human data to create a taxonomy, how about we get caregivers, feed care recipients? We actually record that interaction and find out, like, from that data, from their motions, from different features, and can we get a reward function? Can we engineer the reward function from that? So using inverse reinforcement learning techniques and things like that. Yep.
That's super cool. Personally, I feel like inverse reinforcement learnings is gonna take is gonna make like machines and other robotic systems. It's gonna take them to the next level in terms of human interfacing.
Yeah. Now there's a complementary thing where someone may say, okay, okay, I don't care about there may be a reward function. I don't care. All I want is from the direct data, I want to be able to imitate, right? So yeah, maybe you use imitation learning, or maybe use a combination of it. Maybe you use imitation learning to boost your RL or IRL or something like this. So there are so many different things to explore. And again, it's very interesting field. Yes, I totally agree with you.
Yeah, this is a lot more rich than people might think at first. Like you were saying, like, oh, the task of feeding is simple, but
yeah. Exactly. I mean, like, it's just the interesting thing about this task is everybody can identify with this task, And they think it's like it's pretty simple because they are feeding themselves easily every day. But when you go deeper, you see how interesting the problem can be. And there are so many research questions that can come out of it. Yeah, that's exactly why I really love this particular application.
For sure. I think one of the weirdest things about people and computers is computers can do tasks that we find very difficult rather easily. Like they can be represented simply through algorithms, but a lot of the complex things that we do are very complex for computers to do. Do you have any kind of intuition on why that?
Yeah. So I actually had a slide, which I don't have right now, but where basically I was showing exactly that. Where basically I was just saying, I mean, right now probably that is not the case, but I would say a few years back, do you remember the first time when we had an AI defeat Gary Kasparov on chess?
Yeah, Deep Blue.
Yeah, Deep Blue. But now you know how that worked.
Yeah, it was like using a recursive. It was like searching.
Yeah, but I'm not talking about the algorithm. What I meant is just to give you an idea of this, exactly the computing versus the human thing.
Yeah.
The AI algorithm could search these huge search spaces. Of course, Go has higher search spaces and things like that, but let's just consider chess right now. And AI could search these search spaces and come up with solutions that the human couldn't do. So AI obviously has an edge in that, right? To be able to do search in these geometric spaces. But do you know how it was actually executed? AI just told the move. And then there was a person who was sitting there who was moving the knight from one place to another. And you as a human may think, oh my God, searching the search space is so much more complicated than moving a bishop or a knight from one place to another. But at that time, we didn't have the technology to do it. A person had to be there to convert that command, the search, be able to move that thing. Right now, the robot manipulation has gone to that stage that we can do it. But the idea is exactly this. Some things that we think, and especially this is why I am very excited about physical interactions. Whenever there is physical interactions with the world, we as humans, we think it's so intuitive because we have been doing these things over and over, which current techniques, learning techniques and other things find it very difficult because it's also very difficult to simulate contact and things like that. But in terms of, if I somehow have somehow model things as a search space in graphs or something like that and searching there, these algorithms can do a much better job, whether it's a Markov decision process or a simple graph where I do A* search or something like that. Probably they will do a much faster job than what a human can do. So it's very complementary. And so this is where I'm looking at that other part where you look at physical interactions to be able to solve these problems.
Sure. I think it's also that chess, like the amount of decisions you can make at each point in time is like 30 or 40. But if you think about the real world, like you have like 600 muscles, the decision space is like so much larger. So the naive approach.
Let's forget about, yes, I agree, 600 muscles and all of these things. But ultimately, right, it's like an inverse kinematics problem where, like, if you think about the action space, like the just end effector action space, I probably have like 3 or 4 actions to be able to pick this up. But if you want me to physically interact with an object that I've never seen before, and it requires a completely different thing, and maybe I cannot even pick this up, I can use some other tool to be able to do that. So for example, say I have a coin and I cannot pick it up. So I push, using the finger, I push it, and then it comes outside the edge of my table, and then I use it to pick it up. So all of these consequences and physical interaction to be able to do these things are very interesting. And these things are open problems right now. People have used traditional techniques, but it's just difficult to kind of, the search space is, exactly as you said, the search space is huge. And in addition, it's very difficult to model these physical contacts. Like, how do you even go about modeling a soft tissue? This is a separate area in and of itself. Like in surgical applications, cutting soft tissues and looking at how those tissues, one suturing or one cutting results in 2 tissues. It's a huge thing. And there are many progresses in computer graphics community, in physics community and things like that, but we are still not there yet.
For sure. So what simulation research is being done at the PRL or in your group even?
We basically use, like for food exam, we tried, but we found that it's just not there. I even talked to Dieter, who's the head of the NVIDIA Robotics, and they are developing their physics simulators, and they also said it's just very difficult. And so they are not trying to go there. They looked, of course, some simple foods they could simulate, but not other things. So for these kind of work, there is just no simulator. We are directly using real world. And that is the challenge. But for some of the other rigid objects, we use Mujoko to be able to do it.
Sure. What kind of technical breakthroughs would really simplify the process?
I think to be able to model contact, like just imagine just modeling friction. Friction is such a highly nonlinear, like a nonlinear entity. There is not a single person who can claim that they have solved friction in the world. Though friction, the concept of friction has existed for tens and tens of years. It's just not there yet. We cannot model, we can of course approximate, right? We can approximate Coulomb friction, this, that, all of these things. But the differences it's different from the real world performance. That's just one example. Ultimately, it comes down to modeling contact. Like think about like an object, like a grape, which has hard skin but soft inside, right? You want to skewer it. First, you have to give a lot of force, and suddenly it lets go, and you just go enter. And the softness is not just a homogeneous material. It's a very interesting way of simulating it. There's so many different directional, non-isotropic modulus of elasticities that probably you need to use to model this. And so it's just very difficult. And even if it is possible, it is computationally very heavy, that to even figure out how the model will react to this skewering, this penetration, how the grape will deform, it may take a lot of time to actually render it, and which may be too late to actually do what we want to do. So it's just a humongous problem.
For sure.
But that's what is exciting, right? For us researchers, we like problems that are not solved yet, because that's where we want to work on.
Yeah. So for simulations, like instead of using computers, is it possible to create how our screen can simulate images of all kinds by starting from the base 3 layers of red, green, and blue and varying those values? Is there a way to create a physical simulator of different tactile sensations using some kind of atomic units like red, green, and blue for texture or force or something?
Yeah, so there is some work going on there, where basically what they're doing is, at least for forces, so tactile is not just one thing, right? Because it has forces, it has texture, as you mentioned, and things like that. And they differ by frequency. So force probably is a low frequency signal, then texture, which is a very high frequency signals, and then thermal, which is a different thing. And so there are some simulation works that's going on where you simulate forces where basically as a mass spring damper system, where say you have a target point and it penetrates a particularly a virtual wall. Based on this, and if you model this as a linear spring, you can tell the force generated as K multiplied by delta X, where the delta X is the penetration minus the wall. And so you can use that to simulate force, just like a spring force, right? So there are many ways. This is a very simplistic model, a linear spring. Maybe it can be a nonlinear spring. It can be a mass spring damper system. So there are many things, and you can have that in every node, like in FEM model, finite element model. So there are many things that you can do to model forces, and people are working towards it. But again, there are some challenges to it, which is like if one link breaks, how do you readjust the links so that the fidelity is mentioned and things is maintained. Having said that, other things like high frequency things are generally modeled, at least in the real hardware. What they do is they have very small actuators that just go up and down in some patterns with very high frequencies, and you can simulate similar effects to figure out rough texture versus smooth texture. For thermal, of course, you can use like the models that I glossed over, like a semi-infinite solid model to model like the heat transfer rate when you touch something. So there is work going on in each of these. Right now, there is no high fidelity tactile simulator. There are still simulators that can simulate forces. May not be for a wide range of objects, but for rigid objects, yes, like Bullet, Mujoko, physics, so many different things. But tactile simulators, right now there is nothing at an advanced stage yet, but I know research groups that are working on it.
For sure. Yeah, that's cool to hear. I think one thing that people wanted us to go over was more about your, like this technical talk was super cool, and I really want to continue talking about it, but I think for the time remaining, people want to hear about more about your personal journey, like especially like how you became, how you got into Cornell, how you got a professorship and stuff like that.
Sure, absolutely. Yeah, I can tell you. So basically, I mean, like so you just like getting into a graduate school, you have an application process. So applications are again due around the same time. So like around October, between October and December, you apply to different universities if they have calls out. So they will have a call out, assistant professor in this department focusing on this, or assistant professor in this department focusing on that area. And if you think there is a call that is relevant to you, you apply. Application is of course free, but it requires things such as you need to, there are multiple steps to it. So the first application, the first set is a written application where you submit your CV, of course, and you fill up their application form. Then you submit something called a research statement, which says what you have worked on in your previously, what you are currently working on if you're a postdoc, or if you're not a postdoc, you're directly applying for a PhD, then you can say what you've worked on previously, what you're currently working on, like when you're applying, and what you are going to work on, like what's your plan, going forward in the next 5 years, 10 years, 20 years, and you need to tell what you are going to work, and so then you submit this research statement. You also need to submit this statement called teaching statement, where you need to say if you have any taught any classes or TA'd any classes, or what are your plans, what you've learned from those, and things like that. And then you have to submit this thing. This has become more and more common as years are passing this, but not every university requires this, which is a diversity system, which is diversity statement, which is how will you make sure that you are going to encourage diversity through your research and service and things like that. So you submit these 3 statements. Of course, you submit recommendation letters. Of course, your recommenders will submit recommendation letters, and you submit your CV and your application form. And that's and of course, some universities may ask, what are your top representative publications? Some people may not ask. So you do this first written round. After that, you hear back. If you cross the stage, then you hear back, and there can be multiple things. There can be a middle stage where people do a Skype interview or a phone interview, where they want to know more about you, and they may ask you some questions there. And then you go to an on-site interview, or some places are there where they directly go from written to on-site interviews. And in on-site interviews, what you do is basically you give a talk, which is a 1-hour talk, and then they ask you different questions, and then you meet with different people in the department that's hiring you. And they will basically you talk, they will ask you questions, technical, your vision, everything. And then after that, if they like you, you get the position, and then you decide where you want to join.
Sure. Also, what drew you to teaching as well as research? Because I think as a professor, you get to do both.
Yes. So what was your question again?
Yeah, so it was like, instead of just being like a pure researcher, what drew you to teaching as well?
Oh, yeah. I mean, I love teaching. I taught a graduate robotics course, winter 29. It was called robotics. It was a CS robotics course. I loved that experience. I loved the idea to be able to share people learn from people, and also the art of developing a course material. You also learn through it. Because once you develop a material, you have to go through it again, and you become more and more knowledgeable about it. And then when students ask questions, you think, I may not have thought about it. So it's a very interesting learning process for me, and I have learned quite a lot. I enjoy teaching, so I definitely want to do both. And universities are for students, right? I mean, of course, and so whatever makes the students succeed in their career, whatever they want to do, we should enable them. So we need to teach them so that or we need to teach, or we need to learn together so that we can, they get some fundamental ideas about things that they want to learn about. And we can also do some things, some research things where nobody has looked at before, and you explore things and you work together with your students to do things. Both of these have some very interesting aspects, and both of these are very rewarding. So yeah, it's just the rewarding aspect that excites me to both of these things.
For sure. It's a great answer. I was also just wondering, like, do you, like in your teaching strategies, do you kind of think from first principles and innovate in teaching as well as research?
Yeah, it's very important, because like it's like even the minute things are so important. So you need to first figure out how to make a class informative as well as interesting. If it's like many people, like people generally who will teach, of course, they will be experts in those areas, but they may not be good teachers, which means that a person who is sitting in the class may not be able to grasp that. If a student who sits in the class cannot grasp it, it's not the fault of the student, it's the fault of the teacher. So we need to be able to make sure that we design the material such that it's interesting to the student, that the student themselves will be interested to look at it. And so there are many techniques. So for a class like robotics, of course, there can be some classes where there will be mathematical derivations where you derive algorithms, but it is also a great idea which I applied, and I saw from my evaluations that students loved it, that you do not just end with an abstract mathematical concept, because then if a student is true roboticist, they'll be like, okay, I learned Kalman filter, so what? Right? And so you need to be able to connect this and show real applications like robots using the technology, like using the algorithm that we just derived and doing cool things. That's when students see, what I learned, not only I learned the depth of it, I also know how it is going to be useful. And it makes the classes more interesting. It makes them grasp those aspects. When I was myself a student, I have had a mix of different teachers, right? And I have found that to be very useful, especially being a roboticist. And so I try to do the same thing. Same thing goes for interaction. You need to be approachable. Someone needs to be able to be free to ask you questions. There are ways to use, when you teach also, even if you have designed the material, there are interesting ways, like when do you use whiteboard versus when do you use slides, versus when you use whiteboard, how do you use it so that it's legible for the person sitting at the back? How do you encourage people to answer questions? How do you make them come to your office hours? So many interesting things. And every time, and again, I am just starting out and I'm still learning, but just from that one course experience, I have learned a lot and I've evolved over the course. Like my first class or first two classes were very different from my last two classes, where I adapted myself by learning from student feedback. So it's a very enriching experience.
So how are you soliciting the student feedback? And also one thing is, how do you gauge the class's context so that you know how to tailor your explanations?
Yeah, that's an excellent question. It's basically through feedback, right? So student feedback, there are of course some formal mechanisms of getting student feedback that UW does for us, like student evaluations or things like normal student evaluations that happen either in midterm if you choose to, or at the end. But in addition, I want to make sure that during the course of the course, like in between, I ask them, what do you think? Is there something that needs to change in the course? What needs to improve? What's working? What's not working? So that's just on me. It's not through the formal mechanism, and you just talk to people. Now, in terms of gauging the class, you just basically explain a concept, and you see, you see if they are asking questions. Because it's almost generally the case that if there are no questions and you are explaining concept, then it's not a good sign, because people are not just being, it's almost impossible that everybody will understand it at first go. So if they are not asking questions, that means they are just being shy.
Yeah.
So then there are multiple ways to figure it out, right? One thing is you can do is in the class, you can always encourage them to say that it's okay to ask questions. And in fact, it is okay. But I have asked so many I still ask stupid questions. There is nothing called a stupid question. All right. It's basically, if you have not explained well, then they have a question, because everybody who's sitting in the class is smart.
Yeah.
So you need to be able to understand that and encourage feedback. So you keep asking them. You look at, are they paying attention? If they're not paying attention, either the topic is boring or they are not understanding it. And you can guess this from their facial expressions of what they're doing and how engaged they are to the class, right? And then there comes a subtle point where some people may want to ask questions, but they may not just be comfortable to ask question in a public way. And that is totally fine. So that's where you encourage people to also come to you and ask you questions in confidence, so that they know that you are a person that is approachable. If they want to ask in front of a class, sure. If they want to ask you separately, that's also totally fine. Ultimately, as a teacher, what it matters is the student knows, gets the material that is being taught. How they get it, it's not really important, whether it's questions to class or questions in a private office hour or something like that.
So what are some strategies you use to make yourself approachable and encourage people?
Basically, like just be genuine, right? And
yeah,
like this is, I truly believe that, and you just be genuine, and I hope people actually get the feeling of that. From me, because if they don't get that feeling, then I need to change something. Something is not right, right? But in general, I try to always encourage them to ask questions. After every topic is taught, I stop for a time. I do not immediately jump to some other topic. I open up the classes for. I want to open up the classes for discussions and things like that. So yeah, those are some things. But you need to be genuine. You definitely need to be genuine.
Yeah, I got that sense from our conversation. You're very passionate about this topic, and it really comes across, which I really appreciated.
Thank you.
One other thing is, just from my personal experience and what my friends have said, is a lot of times, like in classes, people can, like, especially with the imposter syndrome, like certain people can kind of feel like, oh, I don't understand this. I'm an idiot. I don't want to ask for help, or like they feel stupid. Like, how do you reach out to those people and make them feel like they're not stupid and try to help them?
Excellent question. And you know what? The best way to tell them is to tell them that imposter syndrome is not just for students. It happens to faculty. It happens to everybody. Like, it happens to everybody. When I first go, so for example, when I first go and join a new lab, I will always feel like, oh, am I like, do I have imposter? Like, am I worthy to come here? Imposter syndrome, believe it or not, happens to everybody. And so you just need to realize once, and through interactions only, you will figure out that everybody has doubts, everybody has questions, and we are here to solve those questions, or at least try to solve these questions. And if we don't know, we are here to find out other expert sources from which we can learn and then tell you what those sources are. Or maybe sometimes I don't know an answer and some other student in the class knows the answer, and I'm very happy to learn about that, right? And this can happen, and this happens all the time. And so this is not something that yes, I understand that it can happen because you think you are like this or I am like this, but it is much more widespread than what you think. And the point and the fundamental point is, if you have doubts, if you have not understood something, it is not your fault, it is the teacher's fault, because the teacher has not been able to impart it in that way. Now, having said that, there is a caveat. If you are teaching a very interdisciplinary course and you have people from multiple different backgrounds and your course doesn't really have a strong prerequisite, it is possible that someone from a particular background can understand some concept better than other person. But then as a teacher, it's not, again, you should not be ashamed of this, because there will be concepts in that field where the other person who understood this particular topic will not understand. Everybody has their own set of things that they're expert at and set of things that they're not good at. And you need to realize this and take it in a good spirit to be able to learn things. So as a teacher, if you know that, especially in those interdisciplinary classes, we need to do an extra job of reaching out to those students and talking to them and seeing if they're following everything or not. And sometimes even if you reach out to them privately, or they may not reach out, so maybe sometimes they may feel better, like they may feel more comfortable to talk to a TA instead of a teacher. So TAs can play an important role, instead of a professor. TAs can play an important role there as well. Or sometimes they may not even be open to talking to a TA, in which case you can have these indicator tests from which you can figure out from the indicator tests who is getting the concepts and who is not. And then you approach them and take the burden of explaining them to yourself and do this. So teaching is hard, and you have to continuously be observant, a keen observer, to see what people are doing and learn from this and adapt your strategies based on that. But there are so many strategies that exist, and I'm also continuously learning.
Sure, I really appreciate that you're taking the personal responsibility to reach out to students. I think that's great. And also, like, the fact that you said that even researchers and professors feel imposter syndrome. I mean, personally, I mean, I find it, it's hard to wrap my head around that. And I think a lot of people, but
I'll tell you this, right? Let me give you an example. Say a professor, when they become a professor, like say, so like generally the way our education system is arranged, like if we are in undergrad, we study a lot of things, like it's about breadth.
Yeah.
Like masters, it's a little bit constrained, but it's still about breadth. PhD, it's about depth. And then you do postdoc, it's even more depth. So see what's happening. You are definitely becoming an expert, probably a world expert in that particular narrow area that you are working on by the time you are becoming a professor. But there are so many other areas that you don't know. Probably you don't even know some basic stuff. So if you are in a meeting where you have multiple people from different backgrounds and they're talking about different things, there will be many topics that you will not understand. And you may feel like, oh, there is a big gap in my knowledge. But the point is that, again, you are an expert in one category, but it is always good to explore, but you need to acknowledge that and use that experience as a way to learn, to cover that gap. If you think you want to contribute, if you really want to spend time on it. If you don't want to spend time on it, yeah, there is a field. It's an excellent field. I'm not going to focus on it. I'm just going to accept that I don't know. That's fine as well. Like there are many topics in computer science or in other branches of engineering which I have practically no idea about. I know those fields exist, but I do not want to focus my time on that right now. And so it's okay to accept that, right? But if I find a gap in an area that I'm interested in, and I may feel that, I don't know this, then it's okay to accept it and then work towards covering that gap. So let's just use that as an indicator to, as a positive, to work towards it instead of feeling down because everybody has some areas that they're good at and some areas that they're not good at.
Yeah, that's great advice, because I know a lot of people can have imposter syndrome and then think they're not good enough and give up, but really, yeah.
Never. I mean, do the thing that you like to do, that really encourages you, and automatically you will see that you will automatically, because you love to do that, you will keep working on it, and you will become an expert. And all you need to do is become an expert in one thing. And then for other things, you can have a passing knowledge. That's fine. Of course, if you want to have a pursuit of knowledge in many different things, that's a great thing to have. But just saying.
Yeah, definitely. I think a lot of our listeners will appreciate that.
Cool.
The kind of last question or discussion topic I wanted to go over was education innovation, or specifically with robotics. Like, is there any like specific research that's being done on how to educate people about robotics and different strategies? And I just want to preface this by saying, right, like you could think about the different strategies of education as it's like a space of different strategies. And the current way is just a single point in that space. And I'm not really sure that point is like an optimum. So like what ways do we have of moving towards more optimum education strategy just in general, and maybe for robotics specifically?
Yeah, sure. That's a great question. Actually, since you mentioned this is the last question, I just want to make sure, because I see Jason is here. I just want to make sure that, Jason, do you have any questions for me? I'm happy to answer.
I do have a few questions.
Oh, please. Then Saket, do you mind?
Yeah, definitely. Go ahead, Jason.
Yeah, maybe I can answer Jason's question first, and then I'll come to your last question.
Yeah,
Okay.
thanks for including Jason.
So I appreciate your patience and great talk, and for sticking around so long to do this Q&A. So my question is, I'm an EC student, and I've taken a few classes in robotics and controls and signal processing.
Cool.
And a lot of the code I've written has either been Python or MATLAB or
Right.
Simulink.
Right.
And I know that you can't, like, on real systems, on real embedded systems, on where hardware constraints are real, and you'll have to deploy, you're going to have to interface with hardware and sensors that don't have a nice drivers written for them.
Right.
I don't have a lot of experience on writing software for the real world, as I will say. Can you recommend any background or texts? Or...
Sure. So by the way, first of all, I'll say that what you have learned is also very relevant. And real world systems use a combination, at least most widely used real world systems use a combination of Python for higher level libraries, and for those low level interactions with drivers or actuators, they use C++. Having said that, of course, for even lower level embedded systems and things like that, or writing drivers and things like that, in a very low level, you can use even like some assembly code and things like that, but nobody does that these days. Okay. Most of them are focusing on Python and C++. Having said that, there is also a lot of research groups that work with MATLAB as well. And as you probably know it better than me, MATLAB Simulink has this RTW, real-time workshop, using which you can connect whatever things that you build, and it will automatically generate the C++ code from your MATLAB Simulink diagram or something like that, and interface with real systems. And so there are ways that what you are currently doing is actually very relevant anyway. Having said that, I would say, again, looking at widely used systems, Python and C++ are probably the most widely used systems. So you should, if you can, definitely get experience in those coding. And another thing to focus on is ROS. This is becoming really popular these days. It's called Robot Operating System. You have both Python as well as C++ interfaces for those. So ROS tutorials are there. Definitely learn those. This will be super useful for you. The ROS, basically the purpose of ROS, it's, even though it says ROS, Robot Operating System, it's not really an operating system. It's more like a framework. It's a communication protocol communication. It basically has a hardware independent communication way to communicate with actuators and sensors. So using like a master model where you have a ROS master and you have publisher subscriber model. So you publish certain data, so for example, say the actuator, the sensor say will publish some data. So sensor will detect, oh, there is a monitor here, and it will publish that data. And then the actuator will subscribe to that data, and it will say, oh, there is a monitor there. I now know there is a monitor there. And so, and then the motion planner can use that algorithm, to figure out, okay, I now need to avoid the monitor. And then the motion planner can decide something and, like say, generate a trajectory, and then it can publish that trajectory, and then the actuator can subscribe to that trajectory and actually execute it. So basically, it's a publisher-subscriber model. It has also other models like service models, action plans, and things like that. But the idea is that the hardware, the sensor hardware that you're using, or the robot, the actuator, and everything else that you're using is abstracted away. If you have a ROS code written where you have a publisher that uses a topic, you can use the same ROS code to try out a different sensor as long as the topic type, the message type matches. So it helps to come up with a code that is more generalizable across multiple robotic systems with some tweaking, of course. And it has really helped in democratizing robotics. Earlier, before ROS, there used every lab used to have a separate code base. So definitely learn ROS. And it's mostly used for interfacing between sensors, actuators, basically for communications. So ROS, Python, and C++, if you're good at this, and of course, Linux. Linux is fundamental to all of this. You are, I think, golden. You are all set.
Okay, I appreciate that. In your research or in your experience in general, how important has it been to optimize code for performance or for like multi-threading or parallel?
Excellent question. That's an amazing question. Many academic labs just prototype systems. And so if you just prototype systems, the code is obviously not very well optimized. But in our current lab, we actually have a standard which is very close to industry standards, where you submit a code, there are other people who will review it, you create a pull request, other people will review it, you do multiple iterations, and then only you basically merge it to a master or something like that. And so we are pretty strict because we are developing a robotic system that deals with real people in the real world. And so we need to be extra careful about our code and what its real-time performance is, what the safety implications are there any bugs, anomalies, edge cases, and things like that. So, but I would say our lab is kind of an anomaly in the space of academic labs, because there are many labs where you just prototype systems, you implement an algorithm, do an experiment just before a paper deadline, see if the experiment works, and then you are done. And it's very difficult to port that particular code when a new student comes in. But this particular lab is different. So I guess it depends on the lab.
The latter has definitely been my experience.
Yeah. I totally agree. I mean,
especially with machine learning.
yeah. It's the majority of academic labs. That's how it is, unfortunately.
Would you say, is there an easy way for an individual to acquire some of those skills?
That's an excellent question. I would say first step, of course, is select. Like when you select a lab, look at what their philosophy is, what they do, ask them these specific questions. Even if you say you end up in a lab which does not do it, you can always do industry internships. First of all, you can start this culture in your lab. But many people may not be okay. They may say, I am here to publish papers. Doing good software engineering is just it's going to reduce my output rate and things like that. If you have lab mates or if you have lab culture like this, you are out of luck. In which case, basically what you do is you, of course, try to learn yourself these different techniques and do industry internships, especially focused on these kind of software techniques where you pick up these techniques and you can use it yourself.
Okay, thank you. And I guess I had one more question, which was, sure. It seems a lot of jobs in robotics and is the area in general seem to have place a significant emphasis on having a PhD or pretty advanced education. Do you have any advice for undergrads who would like to get a job in this area? I guess.
Yeah, I would say actually, like some robotics research labs, yes. But there are many robotics startups and companies that are looking for engineers or computer scientists, and they employ undergraduates all the time. If you're talking about industry, academia, of course, an undergrad can join a PhD or a master's program, so that's also definitely possible. So you'll have to just look at the right industry. I personally know multiple startups or companies that are totally fine. Like they are very happy with hiring an undergrad, and there are many projects that are specifically meant for undergrads. But if it's a research lab, that's when that question comes here, where probably they would sometimes they will have a call that is specific for a PhD or something.
I see. Okay. I appreciate your input. Thanks for your time.
Thank you, Jason. It was great talking to you. Saket, so yeah, coming back to your question about education. So yeah, it's a very interesting question. Like the way we work right now is basically trying to make robotics, democratize robotics more. So you can do that in multiple ways. Developing easy kits where people can try out these different concepts without a lot of investment. We do a lot of outreach. We go to high schools. We organize tutorials. We bring in people to show demonstrations and answer questions and tell them what to focus on, like for example, what courses of studies to do and things like that. So it's basically everything comes back to the original question of awareness. Make someone aware, like get them aware so that they know that a field like that exists. What are the opportunities and how do you like what are the right ways, like what are the different steps that you can take to actually achieve that. Having said that, there is actually a thing that has started which is called a National Robotics Week. UW doesn't really do it. Unfortunately, when I came in, I asked, but my previous university, Georgia Tech, does it, and other people do it. And so if you guys are interested in robotics, you should definitely talk to your admin or your advisor to be able to organize this. Basically, the idea is this National Robotics Week, all the robotics labs across campus, they make it an open house. And so you bring, and people, students, high school students, middle school students come from all around the state, come and see this, and you educate them about robotics. You can organize tutorials, you can organize competitions, you can even just give demos and talk about robotics in general. So I think outreach, through outreach, we can create this awareness and then figure out what are the right courses and basics so that they can have these basics to be able to pursue these courses or this line of work. But it's very interdisciplinary. And so there is no just one solution, because anybody from any department can contribute to this robotics field, because it's inherently a very interdisciplinary field. You just need to find a project that's looking for your expertise.
Thanks for that answer. Jason, do you have any other questions?
No, I owe you a shout out for getting Uber to come to our campus, Tapo. I got an interview with them.
Oh, awesome. Yeah. Awesome. Good. That's great. That's awesome. I'm glad it worked.
Sure. Thanks for your time.
Yeah, thank you. It was awesome chatting with you guys. And again, feel free to reach out to me via email. And again, if you're interested in working with me or working on the problems that I'm interested, like, on similar kind of problems, feel free to reach out because I'll definitely look out for students starting next year. And feel free to reach out to me via email. Saket, you can give people my email, and I'll be happy to take the discussions from there. And also, regardless of that, if you have more questions or different questions about the question about following a robotics career, robotics jobs, or in fact my work as well, any questions, feel free to reach out, and I'll be happy to answer.
Sure. Thanks so much for your time, Tapo. This is super interesting, and I think a lot of our audience will find it great as well. Appreciate
Perfect. It was really fun talking to all of you guys. I really enjoyed the discussions.
Yeah, awesome.
Okay.
Have a nice rest of the day.
Yeah, you too. Bye.
Thank you.